So we've done vector addition, but let's now move to vector subtraction. Vector subtraction is just the same as vector addition. The difference is when we have A minus B, it's the same as A plus minus B. So if we're doing A minus B, we rotate this 180 degrees, which is the same as multiplying by negative, and that is our sum. I mean, it's our sum, but it's our minus as well, because our sum is literally A plus minus B. Okay, so doing this graphically, it's quite straightforward. So if we have A12 and B is 3, 1, if I draw these in, and I've taken 2 squares, is equal to 1 unit. So 2, 4, so this will be our A, and our B is 3 across and up 1. So that's our B. But we want to find A minus B. So we could actually draw A up here, and then a head to tail method. We're actually going to rotate that 180 degrees. So here we have it. So A minus B, so the addition of these two. We have A minus B here. And if we look at this and take this as our origin, we'll actually find that this is minus 2, 1. So minus 2, 1. So A minus B, minus 2, 1. We could have done this with the components. It's the same as 1 minus 3, so we're just taking the x components, 2 minus 1, we get minus 2, 1. And it doesn't matter then if we have a pronumeral. So if we had a pronumeral, C minus D, we'd take our components, so P minus W, and 5 minus n. Components do make life so much easier. Now we've just used general vectors, but what about position vectors? So when you're going from one position to the next. So when you're going from, if we let P be a point xy, then the position vector is the vector x1, y1. For instance, if we have P as 4, 3, then our position vector, now this is just taking this as xy, this has got 7 squares across and 6 up. So 4, 3, going across 4, going up 3, going from 0 to P, so our point here is 4, 3. Therefore, our vector is 0 to P, where this is our origin. So our vector looks pretty much the same. If we let Q be the point 7, 1, so Q is here, our vector OQ is here. So that's 7, 1. Now, from the diagram, what is the vector P to Q? So if I'm going from point P to Q, what's our vector?
2 minus 2.
Are you sure it's 2?
3 minus
3 minus 2. 3 minus 2. 3 minus 2 because you're going across 3 and down 2. But if you want to calculate this from these two vectors, how would you do it? Or even from these 2 points? It's actually very straightforward. If you go from P to Q, you're actually minusing. So if we go 7, 1, so that's Q is our end point, and we minus P, our start point, we end up having our vector. So your position vector, PQ, is also the same as saying OQ minus OP. Because if you look at this, PQ here, sorry, I'll use laser. Not that it's a laser, but you know what I mean. PQ here is the sum of OQ, and if we flip this one, flip it around here, then it'll be head to tail here. So it's OQ minus OP is equal to PQ. Have I lost you in the vector addition? No? Good. I'm glad. I know it's early in the morning, so I have to check these things. So the vector from P to Q here, so PQ here, once again, minus the P, so final minus the initial, so it's 4, 4. It's very straightforward. You can just minus the coordinates. Which brings us to standard basis vectors. Standard basis vectors, they have magnitude of 1, and their whole entire purpose in their life on a page is to point. So, can I flip the page? Good. So, these are your basis vectors. They've got one purpose in life and to point. They've got a magnitude of 1. That means if you multiply it by something, it is 1 times whatever it is that you're multiplying it by. So if you have, say, a distance in the x directions, 5 kilometres, times by I, this is your basis vector in the x direction, you're literally saying 5 kilometres in the x direction. Of course, if we have something down here, you would have 5 kilometres here and maybe 3 kilometres here, so it's 3 kilometres I plus, 5 kilometres I plus 3 kilometres J. Or you could have 5I plus 3J brackets kilometres, since they're both kilometres. So in 3D, your basis vectors are I, J, K. I do know some people from overseas might have seen them as X, Y, Z with the little top hats. Okay. They're also known as coordinate axis vectors, and we just use them like building blocks. So another name for it is the unit vector. And these unit vectors can be used to represent your vectors by simply putting the components. So remember 5 kilometres, 3 kilometres. Let's say we're actually going to go up a mountain. We're going to go up. Now mountains are definitely more than a kilometre high. So let's say a 10 kilometre mountain. Okay, so 5, 3 and 10. And that will tell us where we are situated relative to some point on the mountain. So this is the same, that there is actually the same as your x component plus your y component plus your z component. Now, your standard basis vectors can be used as the building blocks. So converting from components here, you're simply multiplying your x component with I, your y component with j, and your z component with k. That's all you're doing. It's not meant to be rocket science, but you know rocket science is not that difficult either. And I have just mixed this up and no one's picked it up. So we've got j and k. Okay. Now the thing about this, by putting it into this format, it makes it extremely easy to add and subtract, because you are adding and subtracting your components exactly the same as what you were doing before, but now you're separating them out into the x, y, and z direction with I, j, k. So here we have a plus b. So we have 2 plus minus 1, I, plus 4 plus 2, j, plus 1 plus 3, k. And the whole thing behind this is to make life easy for you, believe it or not. So it's another notation. So if we're doing minus 2 minus minus 1, I, plus 4 minus 2, j, plus 1 minus 3k, and we have 3i plus 2j. Please make sure you're paying attention to the negatives. Minus 2k. It's nice and straightforward. Now, if you have a unit vector that points in another direction, you can actually multiply that unit vector to get any size vector in that direction. So if you have a vector, you really would like to get the unit vector. That sounds so circular. Okay, can I flip the page? Not yet? Yes? Yeah?
Why do you say A at like the AXI plus AYJ? Isn't it equivalent to I, J, K, then X, Y, and Z?
This is actually just the component. So if I was looking at it generically, I would actually have A1, A2, A3. Okay? I was simply trying to reinforce this, so I really should have my arrows, but what happens is when I convert this from my computer, I lose some of my arrows. Okay, so if you have a vector, we don't know what size it is, but we know it is ABC, you can find a unit vector in exactly the same direction as the original vector by dividing the vector by its magnitude. Your unit vector has a length of 1. Standard basis vectors are unit vectors, which I've already stated, and your unit vectors have a little top hat to indicate it's a unit vector. So find a vector for A. If A is 3, 4, then the length of A is the square root of 3 squared plus 4 squared. So it's just the magnitude. So a vector of length 1 in the direction of A is called the unit vector. And that's going to be A divided by the magnitude of A. So it's 3, 4 divided by 5 And the person who wrote this question had a sense of humour. And this is the same as 3, 5i plus 4, 5j. Now, this can then be used to find a vector of a different length in the same direction. For instance, a vector of length 7 parallel to A would be 7a times by the unit vector. So 7 times by 3, 5, 4 over 5, which will give us 21 over 5 and 28 over 5, or J. Okay.